We directly move on with the next presentation. It's being held by Markus Kett. Markus Kett is working for MicroStream, and he's talking about databaseless in-memory computing, how to, with 1,000 multiplier of 1,000 in speed, how to generate cloud cost savings at scale.
All right. Thank you so much for the introduction. So welcome to my talk. It's all about databaseless. So it is a magic topic. Databaseless in-memory computing, 1,000x faster data processing in memory, and cloud cost savings. So about the agenda of this talk. So first of all, I want to talk a little bit about what's the problem with traditional database systems of today, and why are the cloud costs also high for most companies using the cloud. And then I will explain how we can realize in-memory database processing in memory, how it can be happen that it's 1,000x faster than traditional databases. And I will show a live demo and how you can use it. About myself, so my name is Markus Kett. I'm CEO and co-founder of MicroStream, and we have building Java development environments for almost 15 years now. And we built a great GUI builder. Everything was easy to use, but the problem was when our users wanted to store data or show data on the screen, they were in trouble because database programming in Java is so complicated. And so we started 10 years ago with developing a different approach. It was not our invention, so this concept is already used in practice, but we'll build a framework for that, and it's now developed at the Eclipse Foundation. It's open source now. Right. So today, everybody talks about, of course, AI, machine learning, virtual reality, blockchain, quantum computing. So, of course, every application in the future will have some AI algorithm, and there are 3 critical factors for all of these applications: high performance, low data storage costs, and simple implementation for a fast time to market. And who of you, by the way, is interested in high performance? So please raise your hands. Okay. Almost, not that much. Okay. Who of you is a Java developer, by the way, or developer? Okay, nice. So this topic is important for developers and IT managers as well. So we can realize all of these applications with programming languages because they are ready for that. They are great. They are fast, and we can do everything. Almost all use cases can be realized. So some people say Java is not that fast. Okay, for embedded systems we use C++, but in the end we can build almost all use cases. So IoT applications, desktop applications, boring office applications, but also AI. Everything is possible. The problem is, for storing data we use traditional database systems, and they are slow. They are high complex or lead to a high complexity, and they are very expensive in the cloud, and they are limited. They are built for specific use cases. Let's see why. So here is an architecture overview about the classic application. You can see the layers. In Java, for instance, we have a virtual machine. It's the same in .NET. And on top of that, we have the application. So we can build everything. So great. As soon as we want to store data, we are in trouble. Why? Then we have to use a database. A relational database works fundamentally different from a programming language. Storing objects that we use in a programming language in a database is not possible. They are incompatible. It's the same with NoSQL databases. They introduce new data structure or formats like JSON, a graph, objects, or now the vector databases. They work with vectors. But all of these data structure or formats are also incompatible with the language model of the programming languages. So, but hey, we use databases every single day, so what we're talking about. So this problem is, of course, is solved because we use between the application and the database another layer. We use data conversion or a mapping through every single read and write. And this is the performance killer number one, because creating objects behind the scenes is very expensive and leads to high latencies. And this is with all databases on the market. So you can read more about this in the internet about impedance mismatches. So, but this latencies can be, so we can accelerate database queries by just adding a cache. So in-memory computing is fast, of course, so let's add a cache, a local cache, which means it runs in your application machine. So then database queries will be faster, great, but we add complexity, right? What about distributed systems? And most big applications are distributed systems. Microservice architectures are distributed systems, so the application runs on multiple machines at the same time. So if you change data on one machine, then the machine is in sync with the database. Everything is fine, but the problem is that all the other instances are not in sync with the database, so we are in trouble. But of course, we can solve it. So let's put the cache in between the application and the database. And to avoid a single point of failure in the cloud, of course, we need a cluster. So we use a distributed cache. So we add another complexity, a lot of machines, and then load goes up on the database side. So, but we can solve this problem because, yeah, we can run a database cluster. So we distribute the load through multiple instances of our database. So, and then in-memory data grids do pretty much the same. You can run an in-memory data grid in between, or you can run an in-memory database, which runs also on different machines in between your application and your database cluster. So 3 cluster tiers are running at the same time, and it's not enough, because most companies use search clusters on top of that, so Elasticsearch, for instance. Another cluster tier, another complexity, just for storing data, right? That's crazy, actually. But this is common architecture. With microservices, there is another complexity, because in microservices architectures, we split our features into multiple hundreds or even thousands isolated services, and each service should have its own data storage. And they are all responsible for a specific use case. So if you have a microservice that consumes sensor data, then you should actually use a time series database for that. If you have complex application data, probably you will use a graph database. If you have a microservice that executes an AI algorithm, then you should use a vector database. So multiple database systems in your database application increases your complexity, your effort for development, testing, deployment, maintaining, and of course, this is the reason why your cloud costs explode. This problem is solved. And Databaseless in-memory data processing solved this problem, and this was not our invention. So companies like banks or gaming companies have solved this problem. So because traditional database systems are too slow for them, though they build individual systems, execute all database operations in memory to have best performance. And this architecture is called system prevalence, the pattern. And now there is a framework. So, how does it work? Our programming language, like Java, is only an example. It's really fast. Everything that is executed in memory is executed in microseconds, sometimes nanoseconds, depending on what you're doing. But here we talk about microseconds. With databases, we talk about milliseconds, so factor 1,000. So we're in the programming language, we are mostly 1,000x faster than a comparable SQL query. We have great data structure in programming languages. We have objects. And in memory, we can deal with all data structure, with all types. We can store single values in the memory. We can store lists. We have collections. We can deal with vectors, everything. And we have also complex object graphs with circular references. So this is not a problem. We already have the best data structure, better than all databases. And we have query languages also in our programming language. In Java, we have the Javastreams API. And with Javastreams API, we can search in memory on object graphs, and we can search in microseconds. So 1,000x faster queries in memory. And we have now with the cloud providers a possibility to store data in cloud object stores, and they are 98% cheaper than a comparable database. For instance, a PostgreSQL as a service database at AWS, 250 gigabyte, costs around, depending on the machine, $8,800 per year on only one machine. A binary object store at AWS, like S3, costs only $250 gigabyte costs only $70 per year. If you need more instances of your database, more nodes, then your price will double or triple. So for 6 or 7 nodes, you will pay around $50,000 per year, PostgreSQL as a service. We do not talk about license fees. 250 gigabyte S3 costs you only $70 per year. So that's crazy. And the cloud provider cares for everything. So replication for 99.99% uptime and backups. So that's great and super cheap. So what if we could combine the power of programming language with cloud object stores? Many companies do it already. And now there is a framework we built at the Eclipse Foundation. So the Eclipse Foundation is known for its development environment, but there also are hosted around 100 open source projects, and the Eclipse Store is one of these open source projects. So Eclipse Store adds storage to the programming language and let the programming language care for data storage. And we read data from the memory and synchronize the data, the application data, directly in the cloud object store, seamlessly. And the programmer don't have to care for classic selects. Everything is done with the programming language, super fast in memory. So let's see how this works. So here's a classic architecture. Now we replace data conversion with the Eclipse Store function. Everything is already in memory, so we keep data in memory, process data in memory, so we can skip the local cache. So the architecture gets more simple. And we store data in a blob store. So this is the final architecture. Let's see how fast it is. Performance demo. So here you can see there are 2 applications running in parallel. One is built with a classic Java stack. We use a PostgreSQL database. We use object relational mapping framework, Hibernate, so this is for programmers. We use a EH cache in between, Spring data for querying our database application. And the other application is built with Eclipse Store and uses a blob store like S3. So you can see all queries are sometimes a 10x faster, sometimes 5x, sometimes 100, or sometimes more than 1,000x faster because they're executed in memory. So this is awesome. And you can do it with all applications. So, and we also can build distributed applications and microservices with replication. So we can now replicate the memory through multiple machines, through 100 or even 1,000 application nodes running on Kubernetes clusters very easily with replication. And let's see what happens with our architecture in total. So we replace a classic application nodes with Eclipse Store nodes. Then we can skip the database cluster because we just need S3, right? Fully managed. Everything is already in memory, so we distribute the memory through hundreds or even 1,000 machines. We don't need a distributed cache anymore. We can skip the distributed cache cluster, or we don't need an in-memory data grid anymore. We can save tons of machine computing power. Most people ask, so do we need big memory machines? It helps. So we can now run big memory machines, but you also can use it with serverless Lambda, for instance, with only 500 megabyte machines. This works because of lazy loading. So the cluster infrastructure gets really simple and plain and cheap, and you can. There are two cluster options. You can run it as a Java cluster or JVM with JVM languages like Kotlin, but you can also put the Eclipse Store cluster in between your Python application or a .NET application. This is also possible, and search and query the Eclipse Store cluster just by using REST services. And now we have additional to that, we have Elastic Cloud Service because deploying such systems that scale horizontally easily is really hard. And so we provide a horizontally scalable, scale-to-zero cluster. You can run it on-premise for your own, but you can also run it as a managed cloud service. And then we have elastic scaling, which means if you start an instance of your application in the cloud, you can configure depending on the load, it should scale out. So if the load goes up, because of there are more users, then the environment starts automatically more nodes to handle the load. And if the load goes down, then the infrastructure will shut down application nodes and scale to zero. And then your application cluster runs with almost no costs. So serverless. This is what we call serverless because it scales automatically. If the load goes up, then your cluster will automatically scale out. Again. Yeah, conclusion. And please don't get me wrong. I develop database applications, database tools for developers for more than 10 years. So my team and I, we love database programming, of course. But we have seen it's very complex, and just for storing data, the complexity explodes. It's because of the core problem. The core problem is programming languages and databases. All databases on the market are incompatible. They use a different formats. And so we have to fix it in between. We need a data conversion through every single read and write. And this is the performance killer #1, and this is a problem for the entire software industry. It's for all programming languages with all databases, always the same. So this is the reason why we have this data conversion in between. It leads to a latency. We fix the latency with a cache. The cache adds more complexity. Then we have distributed systems, so we need a distributed cache. Then we need a database cluster, and we need a searching cluster sometimes. So this is crazy just for storing data. And banking companies and gaming companies, they do it differently. So they use in-memory data processing, but they had mostly develop an individual system because they have to implement all database features for their own. So this is high complex, high effort, and nobody wants to do that. With Eclipse Store, now you have a framework. It's super easy to use for developers and enables you in-memory data processing, 1000x faster queries, and you store data seamlessly in a cloud object store. AWS, Azure, IBM Cloud, Oracle Cloud, all clouds provide S3 or similar blob stores, and you save 98% database costs, a lot of CPU power, a lot of energy, CO2 emissions, super popular topic these days, and a lot of cloud costs. So the project is free. You can download it for free at the Eclipse Foundation, and MicroStream is the company behind the project. If you are interested in commercial support, training, or consulting, contact me. We are at the booth. Please visit our booth, and we ask individual questions. Thank you so much for having me. Have a great day at the conference. Thanks.
So, Markus.
Yeah.
Thanks a lot for the insight, Markus. That sounds very promising and like a very concrete business value add. What is the disadvantage? Is there anything one needs to keep in mind when starting to save costs in the end?
No, there are no disadvantages. So all technologies has pros and cons, of course. So we are used to use a classic database. So because we do it for 50 years almost. So there is no doubt we should use a database, of course. But it's the same with quantum computing, so it's a completely different approach. It's more complex, but for developers, it's easier to use. But you have to rethink, you have to think different. So it's a paradigm shift in database programming. So if you talk to database experts, they will not like it. So, but programmers will like it. So, but there are so many pros. And it's used in practice by companies like Allianz, Fraport already. More and more companies use it.
So it's approved in practice and everyone
Absolutely. It's bulletproofed already.
Cool. Very nice. Very insightful. Thanks a lot.
Thank you.